quite nervous and also honored to talk here today because I've never given a talk at a functional, like, programming language seminar like this before, especially with Simon Pekin-Jones and the likes in the audience here. Actually, when Michael asked me to give this talk, I was kind of thinking, why would I even be asked to give a talk here? You know, because I'm really just an object-oriented programmer. You know, that's what I do. I program with objects. But of course, there's some reason to it because I've been doing some work with Erlang over the last couple of years, and so maybe the title of the talk should really be something like an object head in Erlang-lang. I've been struggling with both learning Erlang, but also trying to find business and kind of start turning my big ship. I have a software company. I'm part of a software company where we do lots of Java programming, and it's really a struggle to convince everyone that we should go maybe in a slightly different direction, convince the customers and convince all the employees, etc. And maybe should you do that or shouldn't you do that, and all that. So that's also part of, I'd like to share that story and how far I've come in that struggle. I haven't come very far, but I've made a lot of thoughts about it. So really, when I look deep inside of me, you know, I'm an object head. You know, this is a picture of my brain. You know, these concepts of modeling with objects are really deeply ingrained in me, and I've been severely brainwashed with these concepts when I grew up in computer science. And deep down in the back of my brain, you know, I've really had this tendency to like mutable states. And there's a good reason for that, because I was really, this is the way I was trained, of course. And I like it. So when I started programming, my first programming language was Eiffel, or the first kind of in college like programming language, where I did anything semi-serious, was Eiffel, then C++, and other object-oriented programming languages like Sather, and of course I also tried to implement a compiler for a functional programming language, as everybody does in a compiler course. But you know, these object-oriented programming languages just kind of grew on me, and I was deeply ingrained in this because also the university where I started out was in Aalborg. There's Aalborg and Aarhus, which kind of had these roots in objects because their computer science department was actually, when they launched, they had Kresten Thorup come down from Oslo and help kind of as a visiting professor just to kind of get the computer science department going. So Kresten Thorup, who is really the father of object-oriented programming, being the creator of Simula, was, of course, the supervisor of all my professors. And so in that sense, I was deeply kind of bought into that whole idea of objects. Then, a couple of years into my my studies, I got one of these. It was really cool. They, you know, in America they could make nice and cool things like it's like a Bang & Olufsen of computers. Right? Very nice. Actually, I spent, you know, it was like extremely expensive, $4,000 or something like that. All of my savings went into this single NeXT computer. And guess what? It was programmed with an object-oriented programming language. So I started programming Objective-C. And soon I found out that, you know, I have this tendency when I want to learn something, I like to build one. You know, to learn something, you build one. So I was learning Objective-C, and I found this, because NeXT Objective-C implementation was based on GCC, and GCC is GNU copyleft code. They had to release the code to the open source. So I could actually get a copy of some maybe somewhat old, not exactly up-to-date version of the Objective-C front-end compiler, but there was no back-end. They didn't release that as open source. And actually, the compiler that was there was kind of old, So I had to update that too. So I ended up spending a year in college there, and fourth year in college, doing the GNU Objective-C front end and a new runtime system for that, and getting that all kind of integrated in the CCC toolchain. And in that process, of course, I got very much engaged with folks at Next, so I ended up getting a job there. So they ended up hiring me to be the maintainer of the Objective-C toolchain, and I was there for almost 4 years. But after a couple of years, object-oriented programming was still struggling. Next was new and cool, and we could do like rapid prototyping and do rapid application development for kind of progressive companies that needed new customer-facing features on a really quick turnaround basis. But the object community was still very much struggling for a breakthrough. Next actually didn't really succeed. It ended up, the last year was there, everybody was kind of down and sorry, and we didn't make enough sales, and we were, I think, in many ways ahead of our times in terms of this object. So it ended up, of course, Apple buying it and turning it into an operating system for a phone, and then all of a sudden it was wonderful. But that was 10 years later. So, and the last year was there. One day, there was a white paper that popped in to my mailbox about this new strange thing called Java that they'd done over at Microsoft. No, over at Sun Microsystems. And of course, I was part of the group back then in '95 or something that really took a deep look at this because it was really an interesting mix of lots of known features kind of thrown together, reasonably good, but we didn't take much notice of it back then, not right away. But I was still a bit intrigued. So actually, I left Next because my wife wanted to go back to Denmark. So I figured, I've been working at Next, the greatest place in the world. What do I do if I have to move back to Denmark? So I did a PhD. So I actually. What I didn't tell you before was actually dropped out of college to go work Next. So I did finish my studies and did a PhD, and in that whole phase, I worked on somewhat on the Java generics. I had a little piece of that whole puzzle of Java generics where lots of people were engaged. I was in the standard committee group and had a lot of time doing type system stuff. In parametric polymorphism. So that was an area there. But as I was doing this, I had a couple of students, colleagues from co-students from university way back that started this company, and they wanted to do Java. So I had two friends that in 1996 started a company. They really wanted to do Java, and they were pushing it. It was new and early. It was very much the same field that we have, I think, today, where you really want to go out and push Haskell or Erlang or something, and nobody wanted to really listen to this. You have this ridiculous new programming language, and industry was using, of course, C++ and C, and who would want to program in this new strange programming language? So, so this company was Trifork, my company, that I joined. I bought a third of the company when we had 4 employees, I think. It had already been running for a couple of years, so I'm not technically a founder of the company, but I've been kind of playing around with the founders from the very first day. So I'd like to kind of maybe share some stories on what was it that made objects successful and being adopted, and maybe we could take some of those ideas and apply them again today to help a new technology, the new wave, the new breakthrough come. Because, oh, I got mixed up here. Java gets boring after a while. And actually, because we were there relatively early and we built a group around Java, now all of a sudden we're known as the Java guys, and that wasn't really the intention. We just wanted to be known as the guys who did cool stuff. So now, being a reasonably sized company, now we have 250 employees. We're a listed company. We have offices across Europe and a little office in the U.S. you get kind of big and heavy, and it's really difficult to change things, of course. So I didn't really have a good vocabulary for this, and as it happens, I took, this wasn't because of this, but I took an anthropology class at our local university, like 7 evenings of 3 hours lectures, introduction to anthropology at our local university. It was really enlightening in many ways. Anthropology is really the study of social structures. It's the study of how people interact, how do they organize themselves in groups, and what are the relationships between these people in these groups. How do groups form, and how do they disappear, how do they break up, and so that's really about society, family, governments, all these artificially human-created structures that make up our society. So it was really interesting. You should really go take a class in anthropology. But the story thing that I took from this was really this scourging truth about group dynamics. They tend to brainwash each other. Groups tend to be built around an idea. There's an idea that either attracts people, or people get together and then they kind of make up some idea, because you need to have an idea to have a group. And groups are really important. Like, deep down in our genes, being part of a group is more important than what the group stands for, really. If there's an alternative between being part of the group and not being part of any group, we as human beings tend to just want to be part of the group no matter what their idea is. So it's really a survival gene that we have. We need to be part of a group. But also groups, they tend to stabilize and kind of brainwash themselves to all agree that whatever the idea is necessarily a good idea. You could just take, there's lots of things. You could take functional programming, object-oriented programming. You could take one religion, another religion. Groups stabilize and just tend to end up in this stable state where you have an immune system. You build an immune system in the group that just kind of outs any kind of outliers that don't agree with what the group says. And so it's really difficult to renew a group once you have reached a stable state. And what dawned on me in this class, as I was taking this class on anthropology, was, oh my God, we have a stable Java group, and now, obviously I could see all the signals in our organization. We had the immune system that would push out anything that was not Java. And we had the brainwashing that everything object-oriented in Java was good, necessarily. And I didn't really realize this until I just happened to stumble on this. So what do you do? What do you do when you have a group like this? How do you kind of break out of that? And actually maybe it isn't as bad as I'm saying here, because obviously we're a company where we have lots of new ideas and we're doing lots of interesting things. But I was really afraid that we'd reach that stable state. So one of the things that the idea that we have in TriForm, our idea, our mission is to be in constant innovation. It's to be. It sounds kind of lame, but it's not. Because we want to be at the center of knowledge. We want to be right there where new things are happening, and that's really our idea. It's not the Java thing, as you might think, as the middle managers and new junior developers might think. The real thing in TriForm is we want to be at the center of knowledge. We want to do constant innovation. That's our idea. That's what we're together for, right? Of course, you want to raise attention and cater to this as being our idea, our religion. Maybe it wasn't obvious enough. But one of the things that we do, and we've always done to make this be obvious and be clear that this is our idea, is our 10% rule, which is, Google has a 20% rule, so we have a 10% rule. Our 10% rule says that you have to teach or share knowledge 10% of your time. So you have to be spending 10% of your time giving a class, hosting a brown bag, or giving a little informal talk at lunch, giving a user group speak, being part of organizing a user group, or setting up a conference, or speaking at a conference, or being part of organizing or choosing speakers for a conference, or part of this sharing, part of this building up knowledge and being part of a community where you really encourage people to tell each other what they think is the next innovative thing. Now, of course, it doesn't always play out as everybody using exactly 10%, but generally that's the idea. It actually works out really well. We do have a lot of this going on, and we do have a lot of conferences and user groups and stuff like this going on. In fact, that's become a whole line of business, and it's really for more than one reason, not just being at the center of this knowledge, but when you ask someone, when you go and give a presentation, when you go and talk about a new technology, that's when you really learn something. And I was explaining this to my sister. She's a psychologist and does like business management, fancy business management. She said, "Ooh," so she explained to me. So your company structure is really like a university where they do research-based education. It's very much the same kind of feedback loop. In university, you have research-based education, both because it's good for the professors to actually have to explain this to these students, but it's also good, of course, for the students to get some of the more recent research. So it's this feedback loop. The professors actually learn something by explaining it to the students as well as the students. And it's really a sound feedback way to do new things. And the result of this, of course, is now we're running like 10 major conferences every year. They're called things like GoTo and QCon, and we have a new one coming up called TechMesh that you all have a piece of paper on in your back. So it's actually now really much ingrained, really much part of the TriFork culture to be teaching, to be part of the constant innovation idea, being at the center of knowledge. So, go back to my first slide. I'd like to kind of go back and take a few minutes to discuss what happened with objects and why did they succeed. At least they became popular. Lots of people have been programming with objects and are still programming with objects. Now, I'd like, maybe we can, as I said, maybe we can learn something. Maybe we can take some of their kind of lessons and bring them forward and make that be part of helping functional programming succeed. And I think we can. So, really, object-oriented programming started with these two guys up in Norway. Kresten Thorup, he was working at a union, and he was like a laborers union, and he was working on these simulations of workplaces. So he needed to simulate workplaces and optimize and improve working conditions, and that was really this whole idea of he wanted to make an automated system for simulating things in the real world. So that's the name, simulate. It was a system for doing simulations, so for expressing the situation in the real world and trying to simulate it on the computer so you could improve and optimize things in the real world. So that was really, in that sense, object-oriented programming was really founded in something out in the real world. This was before, computers. Now it's like, over the last 40, 50 years, computers have become the real thing. Right? Before, obviously, the real world was outside of the computers. Now it's inside of the computers. The other kind of major spark in objects was Alan Kay, who was kind of the father of Smalltalk in many ways. And he writes this in his Hopple paper, 93. Each Smalltalk object is a recursion of the entire possibilities of the computer. thus, its semantics are a bit like having thousands and thousands of computers hooked together with a very fast network. It sounds very much like Erlang, doesn't it? Anyway, so I think the core idea here is that objects are these autonomous things. They're interpreters for messages that flow into them. They provide some encapsulation boundaries. You have this idea in my head of an object as an interpreter. It's something that in itself decides how to react to something that comes to it. So if we make another drawing here, we have an object in the middle, something comes from the left here into the object, and then something comes out, and it's the object that decides how this who is interpreted on the left. Actually, this is the invocation syntax in this beta programming language that was also developed here in Denmark. It's kind of interesting. And it looks like a function, but it's a function that has a history. If you put something else into it, it has a history, so something else could come out next time with the same inputs. So, one of the things that I've now been really trying to dive into functional programming, and I've done several different things, obviously mostly in Erlang, but one of the things that really annoyed me was this way of I was missing something. This interpretation notion. See, when you call on an object, you say object.method. You're going to have the object.method with some argument, right? So it's kind of obvious that it's an object that interprets this thing given these arguments. Right? It's a message that's being passed to the object that says, try to do this with these extra instructions. Now, in functional programming, you can't really express that. Typically, you kind of make an idiom and maybe say, we have a function, and then sometimes it's the first argument is kind of the object of what I want to do something with, and then you have the rest of the arguments later. Could be like here. Here's an example. We have a set. You want to ask the set for its size. It's the set. It's kind of the conceptual idea. It's the set that decides what its size is. It's not, in this context, the context decides some function that knows how to compute the size of whatever set is here. And this is a very fundamental thing that it still kind of haunts me when I program functional programming. That I'm missing this abstraction. This abstraction of having a thing that acts as an interpreter, that I can send a message and it can do something. Now, obviously, William Cook did this really good paper called Abstract Data Types Revisited that he published at UPSLA a couple of years back. And here he talks about the difference between an abstract data type and an object, and that they're really he says there's been this misconception in the functional programming world that these two objects are just like abstract data types. But he says they're something fundamentally different exactly because of this interpretative nature. So if you have, for example, you have a set abstraction, it consists of an intersection operation and an includes operation. You can actually implement that intersect operation on one set, and so that you can compute intersection across two different kinds of sets. So this abstraction also hides whatever implementation detail is in a particular set. So you can actually easily combine two different kinds of sets. Whereas with at least a straightforward functional model, it's really difficult. Now I know because I had Simon visiting me, giving a keynote on type classes. That was it. And people telling and everybody saying, yeah, well, you could do kind of this with existentials and type classes. You can encode the same idea. But it doesn't beat, I think, that here is kind of a fundamental and core idea that we have this central abstraction that really is an interpreter for messages coming in. And that's something I'm missing. So I think that really maps really nicely to things in the real world. Right? When if we get back to, I wanted to explain some things about why objects are succeeding. I think this idea of attributing this interpretation nature to things. So we hide implementation details inside things, and this notion of things mapping to objects really is easy for people to understand. And in the object community, we have this notion of conceptual modeling, meaning we actually built a model that lets us talk. This was all the words, say, I had on the first slide. We have an idea of what does it mean to specialize, generalize, what does it mean for things to have an identity, what does it mean to have composition and decomposition, and how does these things map between, say, the real world, the programmer's head, and the program representation. That they're actually between these things, there are a nice correspondence, not necessarily a one-to-one correspondence, of course, but that there is a nice correspondence, and we have a conceptual framework for thinking and talking about this. Another thing, kind of along this, was in the object community, also kind of about the time where Java really had its breakthrough. There was a lot of thinking tools, as I call it, just generalized, ways of representing experience. This was like graphical notations for how to draw an object-oriented program. How do you make a representation of your program that you can draw and share with your customers or share with your colleagues? I haven't really seen kind of coherent graphical representation of how to do functional programming. I'm often missing it. You know, when you talk about function programs with your colleagues, you end up writing a lot of code on the screen on the whiteboard, and I don't really have a coherent and good structure to draw it. I'm a very visual guy. I like drawing boxes and arrows, and those boxes and arrows having some kind of meaning. But I think something that can kind of hook it up to the graphical representation of boxes and arrows, you know, as imprecise as it might be, and as erroneous and, you know, difficult to maintain, it really, having standard ways of doing this in the object world really gave us an advantage over all kinds of other things, because there was nice ways of drawing structure of things. There was lots of other things, of course, that aided, you know, high-level thinking about programs. One was drawing, then there was various patterns, software patterns, kind of standard ways of describing common problems and their solutions in a way that we could talk about. Patterns are necessarily, you know, all these things were overused. UML was overused completely to the degree where people would be programming in UML, and I don't think that's a good idea. Likewise, these patterns, software patterns, were overused to the degree that people only compose their programs out of patterns. But despite there being issues with these things, of course, kind of the casual user of these concepts, these thinking tools, gained a lot of strength, abstraction power, to be able to talk about objects, architectures, structures, and systems, and be able to communicate this to users and other developers and managers, and ultimately the guy paying for the system. So really, I think what it boils down to, that objects succeeded, is very fundamentally that the ecosystem provided ways to really connect the solution to the problem, graphically, verbally, technologically. And at least as I entered this world of functional programming, you know, I haven't seen it all, of course. I've just seen a little corner of it. I don't see an obvious these things obviously popping up in this world. Actually, just yesterday I suggested we should do a UML-like thing for Erlang. so that we could actually draw our Erlang programs in some kind of coherent notation. You should just come in if you want to come in. You don't have to be standing there. Okay. But. Then, also, the object community took a seriously wrong turn. Java was, the first kind of language. It collected lots of nice things from other languages and kind of engineered them together in with some kind of reasonable coherence and a syntax that wasn't too far off from what people were used to. And then they added threads and locks and RPC. And that has been seriously haunting us ever since. Of course, I think part of the reason why Java was successful was exactly because at least it had an answer to these things. In Objective-C world, I can tell you we still don't have an answer to concurrency programming. And actually, my good friend Bertrand Salé, who was he was a senior engineer at Next when I left, and he'd been at Xerox PARC and lots of. I really like this guy. He said, when you go back to Denmark and do your PhD, you should figure out how to do concurrent programming right, because that should really be, that's really something that really needs research. So the wrong turn was that before we really had threads in our Java programs or in our object-oriented programming languages, this way of dispatching messages was actually quite reasonable. See, in an object-oriented programming language, typically the way you call a method, some languages say we send a message, but really what you do is the object has a lookup table inside of it with some names, and then you go find a function and you call that function kind of on the same stack, very straightforward implementation. That implementation of message passing, that's really an implementation of message passing. It kind of makes sense if you only have one thread, because then you can't really see the difference between the message being passed and the method being invoked. Right? So in that context, it really makes sense in Smalltalk to say it has message passing. It just kind of simulates it with function calls, right? Because Smalltalk is single threaded. So there you have it. So the real wrong turn was then introducing threads and locks, but not fixing the message passing semantics to something that makes sense in that context. So, we used to have these nice diagrams of thinking of an object. It's this thing, it has data in the middle, and it has these protective methods around it, right? And if you have more of these, you lose the integrity, really, because the threads just kind of run through these. I think to think of a thread of control is something in itself. It's a little green guy that kind of runs through your object, like this one, right? And then so the method call kind of goes through there, and the little green guy goes like this. So that's the thread, right? Or a thread. Of course, if you have two of these, and you have, they'll run in there and they'll get in a dogfight over who should mutate the state inside this object. So, it wasn't really, Smalltalk was good enough. Actually, it was Java's fault. Java, they introduced these threads, and that's really why threads are so horribly bad, is because they break that abstraction of message passing that really was the core idea in object-oriented programming. So of course, the realization, we've started to realize this all over, and it gives rise to these new concepts popping up in new languages everywhere around. We have functions and data, various ways of doing state containment. Some statefulness is often needed. You need a way to contain it somehow, be it monads or inside a process, inside an actor, inside something else. But especially this process and message, I think, is really appealing to me, and it could be a good way to grab onto all these guys that are object-oriented programmers, because you can actually convince them that this is just another way of doing object-oriented programming. You can take all your core thinking, your ideas, how to structure things, how to architect things, how to build large systems, and actually apply them to process and message-oriented programming. So, how did I get into all this? I mean, obviously I've seen all this across different conferences and places where I talked, but the real issue was that we're building large systems. We're a serious software company, and part of the system that we're building is this large healthcare infrastructure in Denmark, and it really is a software infrastructure. It's something that provides information about drugs and prescriptions to doctors and nurses on a real-time basis. It's a large system that integrates with all the different electronic patient record systems and home nursing, and even the dentist, if you get an injection at the dentist, they have to record all the events that happen that have to do with drugs. So it really became an infrastructure. And so I started looking for something that would give us kind of infrastructure feel to our software. How do we make this structure really be stable? So that's, of course, when I stumbled on Erlang. Or exactly stumbled wasn't right, because, of course, I've already invited Joe Armstrong and Francesco Cesarini and a whole bunch of other Erlangers to come speak at one of my conferences. So I already heard about these things, so I could engage with them. And really, when I started out, I thought that Erlang was a concurrent functional programming language, but it's really not. Actually, I wrote a blog post about this a while back. And when you start looking at Erlang, you'll think it's a concurrent functional programming, but it's really not. It's really an operating system. It's a system for describing reliable computing at its core. That's the design criteria at its core. And then kind of everything else kind of grows out of that. And the concrete thing that grew out of this core requirement for building reliable systems, for being able to provide high availability, was this two-level structure, a functional programming language at the top that describes the behavior of individual processes, and these processes run in an operating system of sorts. So an Erlang system really is a two-layer thing where there is the notion of an operating system, very much like a microkernel system that I was used to programming at Next, or a QNX-based system, if you have experience with something like that. And then the individual processes in this system are written in a reasonably pure, strict functional programming language. So, to learn this, of course, when I need to learn something new, what do? Well, I start by inviting some people to come talk at my conferences, and then I implement it. It's always dangerous. So, an Erlang system looks like this. You run your Erlang program on top of this OCP framework, which is really just a standard library and the operating system kind of mixed in. There's an emulator, and you run all this as a process on top of your favorite operating system. So being an Erlang hacker and object-oriented, being a Java hacker and an object-oriented programming hacker, I had to, of course, rebuild this in Java. So I actually rebuilt the entire Erlang infrastructure in Java. But that's, the details of that are probably a story for another day, given that I only have a few minutes left. So, the main takeaway point from actually this deep dive into Erlang was really, this Erlang thing, it really just is object-oriented programming. Just take that original quote from LNK and just substitute a single word. Erlang really is, at the core, the kind of object-oriented programming system that LNK would have learned. Except, of course, in Erlang, each of these computers, each of these processes that LNK envisions programmed in the functional programming language. And that has a lot of advantages, of course. But now it's kind of, when you have this two-level structure in a system, part of it is in a functional programming language. It has certain characteristics. The other part is actually a very imperative, object-oriented system. It's really good for other things. And part of this, living with Erlang for a couple of years, it's really become kind of deep in me that I really think there's fundamentally two different things that are often confused when we talk about concurrency. I think that there's so much talk, often also at our conferences, about multi-core and cloud and concurrency and parallelism, but I think there's really, you have to make a really clear distinction between these two worlds of concurrency and parallelism. I don't know which word should be on top. But there's a world of interactive systems, systems that kind of interact with the outside world, where the core problems are about coordinating things that come in on different channels, maybe. Typically, these systems are really nice to program with messaging and processes. And at the core of this is the kind of system where I want to understand the parallelism or the concurrency going on in the system. I want to have a mental model of what is the concurrency going on in there. And kind of on the other side of this, I see an equally important trend, and this is where everybody's running. I think it's a pity that not more people are concerned with interactive systems and the concurrency world. You know, these cater really to functional programming, and you can imagine running data parallel Haskell to do a lot of computation, to utilize a lot of CPUs, but ultimately, in this world, you want to not understand the parallelism going on there. I don't care. I just want to use as many cores as possible. But there's, you know, and because this gets so much attention, you know, we often forget that there's actually really good sense in having a sensible conceptual model of concurrency that you can, just like with objects, you can talk about, you can reason about it, you can explain to your customers about the concurrency. We have all these nice values from the object ecosystem that we can bring immediately into this, even though the individual processes are programmed in a functional programming language. So, to wrap up here, we have built a couple of systems with Erlang and functional programming. And one of them is kind of redoing central parts of this central healthcare system that I talked about before. The core issue here was that we wanted to have a distributed architecture, distributed system that would allow us to have a multitude of data centers that each has a replica of the data set, and they can continue operating even if they lose connection with each other. Even if one of them goes down, the other ones can continue operating. So really having a high availability system here. And that, of course, needed some notion of, I mean, it has the built-in problem that you can have data being mutated at multiple places at once. You can have the same patient record being updated in one end of the country and the other end of the country at the same time. And that's where React really came with a nice solution using vector clocks to describe potential write conflicts. So write conflicts in this system are just exposed, essentially, ultimately, to the doctor, just like a software developer being asked to merge when you try to integrate some source code. The doctor will have to approve of a particular merge of records. Say, you must prescribe this drug, but also this drug, and the doctor will have to approve that they don't have interactions. Another system that we built was this mobile platform that we used at Roskilde, the Roskilde Festival here in Copenhagen recently, which is actually, this is a the Relay is a micro version of React that runs on a mobile phone. It's a distributed key value store. It uses vector clocks just like React. So it acts kind of like a single node clustered React. And the really nice thing is that you can synchronize these as many ways as you want. You can do two-way synchronization with all the buddies that you happen to walk by. at the festival venue there. So we use this for content distribution, so to distribute content about news and events. You know, some people would have to get hold of the data somehow by being close to an access point or being able to have 3G coverage. But the problem here is there's so many people that 3G doesn't work when you're at the venue. So somebody from the outside or close to a Wi-Fi point would get a hold of this, and then using, again, vector clocks and a distributed key-value store, you could use Bluetooth or local Wi-Fi to distribute this content across the site. And likewise, users could add user-generated content to the application that would then be propagated to everyone else across the system. So you could register your own events or your likes or whatnot. So it's kind of, you could say it's a Twitter without the need for an internet platform. So I really think, in general, I think I'm really relieved that we kind of passed this mainstream phase of Java. You know, I think we're going into a post-mainstream phase now. No. Post-mainstream is we're through this ice winter of everybody having to program in Java and C#. You know, we can there's so many ways that we're relieved of this straitjacket now, because most software is actually being written behind a web service access point, or it's sitting. You know, there's so much software that's running behind a web server where you really have much more freedom to choose your implementation technology. And I'm really happy that we're seeing kind of this widespread, many different technologies popping up, and we definitely see a lot of interest. You know, running the conferences that we do, there's actually people coming and interested in actually using all these new technologies, these new functional programming languages, or old ones. There's lots of things kind of stirring just these years. Exactly because Java is hitting this wall of concurrency and parallelism. So we're actually building a conference for this. In London, this is my talk today. In London, December, we're doing a conference. We call it TechMesh, but it's really a conference on new technologies. It's on functional programming, and it's on NoSQL data stores. Kind of technologies that push the boundary and go beyond this kind of ice winter we've had, this mainstream ice winter of Java and SQL databases and enterprise technologies. So, I'll just close with saying, you know, I really think this distinction between systems that just compute and systems that are interactive, I think that's really, really important. And if there's one kind of fundamental thing I've realized in these 2 years of being with Erlang, you know, interactive systems are very different. And they probably warrant having different technologies for implementing them. And they are just, by their very nature, they have this immutable state somewhere in there, because they need to maintain a model of something that's in the outside world.